Okay, hello everyone, good morning. I'm going to talk about an end-to-end system for large-scale peer-to-peer MPC and also low bandwidth protocol for weak participants that will support that system. As we all heard from Shai this morning, secure computation is now being used in practice. It's ready to be used in practice. It's being used for key and biometric protection, for processing of encrypted data, for secure statistics, and it has the potential and is ready for many, many more use cases as well, which is what Shai argued this morning. One specific example that I want to give was a recent study carried out in Boston on the gender wage gap. And they actually wanted to get real information about wages of men and women in similar positions. And they did this by asking companies to provide information. Of course, no one wanted to give it because of the sensitivity of that information. And but they managed to bypass all the legal problems by running an MPC computation, which is an excellent example of something that we can really solve that has social benefit. But all of the use cases that Shai mentioned, Shai was arguing for other use cases, but the use cases that he mentioned where it's actually being used, and the other examples that I could give are all actually B2B or maybe B2C examples. We're talking about businesses running MPC between them, or maybe between them and an end user, but that's not actually what we think about when we talk about MPC. The basic MPC promise, the fundamental promise of MPC, is the ability for an arbitrary set of parties, that means us, anybody, any set of parties, end users coming together, really a decentralized peer-to-peer-like setting, being able to compute on their own private data, and for them to get the results, so they get the utility from their data, which is almost the opposite of what's happening today when we're giving our data to Facebook, Google, and so on and so forth, who then utilize it for their benefit. To be fair, we're paying for our services with our data. That's the payment, that's the currency that we're using. But if I don't want that model, and if I want to be able to actually get utility, I'll get the utility from my own data, that's something which doesn't seem to be possible or doesn't seem to be happening at the moment. And the question I want to ask is, why don't we have peer-to-peer MPC? And citing from Shai's talk this morning, it seems that the technology is ready, so what's the obstacle? Why aren't we seeing those sort of use cases also being close to realization? So here are some of the obstacles we have to getting a peer-to-peer or decentralized type MPC. Some of the questions are technical and some of them are deeper. The first is seemingly just very superficial, but it has to be overcome. How do we actually get those decentralized parties to agree on what to run, when to run it, in what environment? How are they going to deploy the software? How do they agree who joins? That sort of platform has to be built, and it doesn't exist. Another thing which is actually fundamental, though it sounds rather silly, all MPC software today, or almost all, is built for its client installation. It's software that you install, but end users don't install software. They run mobile apps or they run from their browsers. And in fact, in the Boston study, because they knew that none of the companies would install software and they wanted them to, but they refused, they uploaded secret shares of their data from their browsers, because that's all they were willing to do. And they had a couple of servers running the MPC because these companies would not be willing to run the MPC themselves. So that's not something which, so if we want MPC to actually be run in a decentralized setting, we need to solve that as well. Almost all MPC protocols require all the parties to be online simultaneously. If we want to run a truly decentralized MPC, we're going to have people in Australia, in Hong Kong, in Israel, and in the United States, and in Europe. They're all in different time zones. And when I go to sleep, I turn off my mobile, or I may not be connected. Some people turn off their mobile. Some people say, no, who turns off their mobile? But some people do turn off their mobiles when they go to sleep. And then it's not going to be running. How do I make sure that everyone's going to be online? Or maybe I'm in the train at the moment. I'm actually just on the train at the time that it's going to run, and I don't want to run this MPC via the cellular network. The high bandwidth of many MPC protocols is also an obstacle, because if we're going to run from our mobiles, there's actual financial cost in using a cellular network, possibly. There's also an issue of stability. Uploading a lot of data, downloading a lot of data is going to be a stability issue. So a much better gender wage gap study would have been a decentralized one. We wouldn't have all the legal problems and have to work for months trying to get the companies to agree to upload their data. It would be much better if people would just participate in the study by each one uploading their own salary and carrying out a study that would be more geographically diverse, be easier to carry out, but for that we need to solve all of these problems and more. So in this paper we present we call it MPSAS or MPC system as a service. And it's a system which is designed to enable peer-to-peer decentralized MPC to run. And it works the way that modern software works. So end users run the software from their browsers or their mobile apps. And I want to stress they're running the MPC itself. They're not uploading secret shares to some small set of servers who they have to trust, but they're going to actually run the MPC from the mobile or browser itself. It's a service model. So you have a cloud service provider who offers an MPC service, and you have subscribers who can purchase or use the service to initiate MPC executions. Crucially, you don't have to trust anybody but yourself because you're actually running the MPC. You don't need to trust the service provider or the subscriber. Of course, this requires that we have software that's been externally validated, but you do that once. And then you can trust that once this mobile app has been signed, you can trust that now it's running a secure protocol, and you don't have to trust anybody else. They're just there in order to orchestrate and not to run anything themselves. So what are the components of this system? There are three main components. The first component is the largest component, is an automation backend. And this is a fully automated MPC execution environment. It was actually built initially by us to run MPC experiments in a very efficient and easy way. So instead of trying to set up manually 100 different servers in 15 different regions of AWS and install software in all of them and coordinate them beginning the execution and then going back to everyone to get the results, which is a huge headache, we wanted something that would do this automatically. And this is of independent interest to the community to carry out MPC experiments. So that's the core of the back end of the system. The capabilities are you can use it to automatically set up parties in the cloud, in AWS, Azure, and so on and so forth. We had it running in AWS, and one of the questions we got from a reviewer was how tightly coupled is it with AWS? What would happen if you wanted to run on Azure? So we got that question, and Lior, one of the co-authors on the paper, took the challenge, and in less than 2 days, he had it completely running on Azure, meaning that it's not tightly coupled at all, and it's actually a general tool. It can be used for multiple execution coordination. So you can actually bid for instances. So you'll get cheap instances to run the protocol. It will then set up the parties automatically on those instances and at the end tear them down so you don't have wasted resources. It will also collect any logging or auditing which is done on those parties and collect the results. You write a script that defines the number of parties that you want to run, their geographical locations, the type of machines, the number of executions you want to run, which protocols or which circuits or code or whatever it is, and then everything happens absolutely automatically. So it's great for experiments, but it's also a great tool as an automation backend to automatically deploy peer-to-peer decentralized MPC. And it works for arbitrary protocols. We already have about 10 incorporated into the system, and we're working with others to add more. So this is the way the backend looks. You can have a look here that you have some code in a GitHub that's via the experiment UI. That'll be downloaded. You set up the experiment, which includes getting these AWS Spot instances, for example. The software is then installed there automatically, the VMs, to get protocol parties. They then run that protocol between them. The results of the experiment are then compiled and sent back. And at the end, it's all torn down and the experiment is complete. And all this happens absolutely automatically. That's the first component. The second component is an administrative component. If we want to be able to run these MPC executions, we need someone to orchestrate orchestrate it, because otherwise the parties can't get together. So here a provider or anyone running this open source will manage the execution. They'll publish an invitation, maybe on LinkedIn. Let's do our own gender wage gap study of computer security researchers or professionals. And via LinkedIn, anybody can join. The administration component will track how many users, potentially which ones, have registered. I want to stress that the system is not aimed for anonymity, but rather of privacy of the inputs. And there's a reason for that. If we want to run an honest majority protocol, which is the one that actually we're looking at because of the low bandwidth, then we need to make sure that an attacker can't just automatically, pretend that he's 1,000 parties and then get a dishonest majority in that way. So actually authenticating to the system is something which is important. The system will then obtain the results, and it's linked to the back end in order to carry out that automatic deployment. And we're going to demonstrate this briefly on something we call private poll, which is a system for generic end-to-end private polls or surveys via MPC. I want to stress that the application itself is not important. It's really just to demonstrate the tool and how it would work. So it has an administrative component. Here you have an administrator page. You can see which different polls are running. There's one salaries or mortgage debt, academic career path. You can see when the execution is supposed to run. You can create a poll over here and publish it. And then there are also other pages here to track the users and so on and so forth. That's the administrative component. It's more of a UI, but the important part is that it's automatically linked to that automation backend. The next part is the end user. This is a mobile app. So you first, on the left-hand screen, the first thing you do is log in. This is logging in via Google or Facebook. It's a problem for me because I don't have Facebook and I don't like to use Google, but most people could get by. But you can do anything. Of course, we don't really care what the authentication is. Then after that, you get a screen which tells you, these are the polls that are running. Do you want to join any of them? You choose to join one, and then you get the information about that poll. And if you want to join it, you get to the next screen. And this is a very, very important screen. One of the big problems is how do we make sure that everyone's online simultaneously? And we have an extremely simple but powerful solution to that problem. And it's not a cryptographic solution. It's really an engineering solution, but I think it's significant. And we asked the user, can you guarantee that you're going to be online, or may you be offline? And if you're going to be online, then fine, you'll run it from your browser or from your mobile app. But if you're going to be offline, then you get the next screen, which offers you two options. One is to use a hosted instance, which means that me as the provider will automatically give you an AWS instance in your name that you will upload your input to. It's not great from a security perspective, because if I really want to, I can go and as a provider, I can break into that machine and have a look at your input. But maybe you work for a public university in the United States, and anyway, anyone can go to a website and check what your salary is, so you don't really care, but you want to participate, so you can just use a hosted instance, or maybe that's not so sensitive for you and you don't mind using that. The other possibility is you can provide your own instance. So you have your own AWS account or Azure account or whatever it is. You can connect your own instance, and then that will run, and you don't have to be online because it's a VM in the cloud, which is always going to be there. So we don't have a problem of being online or offline. If you're going to be online, this is the way it looks. That's just the flow. You see, you get a reminder 10 minutes beforehand that the MPC is going to begin. Put in your input, it runs, and you get the result back, and that's the end of the flow. So this system actually gives you all you need to run an end-to-end decentralized MPC. And the type of flow that we've demonstrated, I think, is very, very powerful and can help us to use MPC to solve social problems or do social research that starts at the end user, which is something that we really want to do. And again, that's what Shai talked about this morning. But there is a cryptographic challenge as well. And that is the bandwidth constraints are a huge concern in such a setting. As I mentioned, actual cost of upload, download on cellular networks possibly, and also a higher chance of failure. So we're considering an honest majority setting, actually specifically a 2/3 majority setting, and it's appropriate for the type of true end-to-end system we're talking about when you have authentication, which is fine for what we're looking at. And we present a protocol in the paper called HyperNPC. It's a very lightweight protocol. It's based on the protocol of Berliova, Trubaniova, and Hurt from TCC 2008. And that was actually the first protocol to have true linear communication complexity overall, meaning that each party transmits a constant number of bits or field elements per multiplication gate, irrespective of how many parties. Even if we scale to 1,000 parties, I'm still going to be sending the exact same number of field elements per multiplication gate. Their protocol has some expensive elements, so we're allowing abort or a not guaranteed output delivery. We can also have fairness for pretty much the same cost. And by removing all of that heavy machinery, we can get something which is much, much more efficient in practice. So the properties of our protocol are, firstly, it's secure against malicious adversaries with up to a third of the parties being corrupt. It's about 4 times faster, a little bit more than 4 times faster than the original protocol from 2008, which is very significant in practice. And in fact, each party sends exactly 13 field elements per multiplication gate, and that's it. Doesn't matter if it's 10 parties running, 100 or 1,000 parties, that's going to be the communication. And the protocol is perfectly secure, which you may think, who cares about perfect versus statistical security? But most statistical protocols, all that I know of actually, have this property that you have an error rate which is 1 over the size of the field. So if you're using a small field, you actually have to repeat numerous times in order to reduce the error rate, and that raises the complexity. But with a perfectly secure protocol, there is no error rate, and therefore you're still sending 13 elements per multiplication gate, even if you're using an 8-bit field. And that is very significant in practice. So here are some experiments that we ran. This is a real statistics computation. This is the one that Shai mentioned this morning. So we have 4 million inputs. It's 2 million pairs of values, 6 million multiplication gates. It gives you mean, variance, and linear regression. It's only depth 1, but that's all you need for the statistics computation. And this is running, for example, on a 31-bit prime field. And it's 5 seconds for 10 parties and 45 seconds for 150 parties. So when I want to do a true decentralized computation, this is quite a large statistics computation. 45 seconds is definitely reasonable, and we can do minutes and numerous minutes without any problem. So this shows that it scales and is actually very, very viable. What about comparisons to prior protocols? So at Crypto 18, the best best honest majority protocol that is in existence by Chita et al. That protocol is stronger in the sense that it's guarantees security up to half the parties being corrupted. But I want to compare the efficiency, not in the sense of saying this is better. This is a circuit with 1 million multiplication gates and depth 20. And I'm looking at 3 different field size, 61, 31, and 8-bit fields. The 8-bit field, by the way, GF2 to the 8, is very useful because you can embed Boolean computations trivially inside GF2 to the 8. And that means you can run Boolean computations, comparisons, and so on and so forth without any problem. And the results are, I think, say a lot. For GF2 to the 8, we can do 120 parties can compute 1 million multiplication gates or 1 million AND gates if it's a Boolean circuit embedded in 1.5 seconds. By the way, this only goes up to 120 because you need the field size to be at least twice the number of parties. So we couldn't go beyond 120. For a 31-bit field, it's 6.5 seconds for 150 parties. And for a 61-bit field, it's 10.7 seconds for 150 parties. You can see that the top line here, the blue line is the paper from Crypto. The red line is our protocol. It's actually the same complexity. But it's the same complexity on a large field. On a smaller field, the paper from Crypto requires repeating a number of times in order to get back to the correct error. So it would be at least as expensive as the large field. Whereas here we can see that the 31-bit field is much less and the 8-bit field is much, much faster, and that is enables us to get 1.5 seconds for 120 parties is very surprising. I mean, if you had asked me 5 years ago, had that been possible, I would have said I doubt it very much. We also ran in other environments. So we ran for a very small number of parties just to see that it runs in the browser and in mobiles and Raspberry Pi. It all runs. There's a lot more work to be done here in scaling up these type of experiments. Actually, I want to talk about that here. How do you run a large-scale mobile experiment without convincing 150 people to install your mobile app when there's probably people who are very security aware and asking you, what do you have in that app? So it's a bit of a challenge. We found a cloud called Scaleway. This is a cloud for ARM, so it enables you to actually run these experiments. It's an IoT type cloud, but they're not designed for having large numbers of parties. So we got 15, now we have 40, but there's some technical problems with getting the experiment because there are technical problems there. But here we can see that 15 parties, they're relatively weak, 250 megabit connections. They can compute the million multiplication gates, depth 20, 15 parties in 40 seconds, 3 parties in 5 seconds. Again, more work needs to be done to check at scale of hundreds and thousands, but that's where we want to go. So in conclusion, peer-to-peer MPC is feasible today. It is possible to build a system that solves all of the technical problems with automated deployment, offline, online execution modes, execution by users on platforms that they're willing to run, like mobile apps and browsers. We have fast enough protocols that can support a large number of parties. Again, the bandwidth scales very, very well here. You are going to be sending 13 field elements per multiplication gate, even if there are 10,000 parties or 100 parties. And HyperNPC is a good candidate for that. And future work will be improving the admin and end user components and doing the engineering work, which is significant, to have the whole system scale up to thousands of parties. Thank you very much.
We have time for questions. I think I'll start with a question. I guess that's prerogative of So I have a quick question. Maybe I have a couple questions, but I'll limit myself to one for now. So it's a non-technical question. One of the things that I kept thinking about during your talk is that B2B applications versus P2P applications, and one of the issues is for salary data in particular, I would kind of trust the input provided by businesses more, especially for a politically sensitive question like that. I mean, you might imagine users can just sign up and give garbage that would totally throw off the computation. I'm just curious your thoughts about that in general.
So it's true, and that's why we're thinking about authentication to the system. For a salary survey, if I had a LinkedIn group of security professionals, and we as a group have an interest in understanding, for example, what salaries you should be expecting or whether there are problems and issues, then we would have interest to provide correct inputs. It's possible also adding things like differential privacy into the computation to remove outliers. I'm not sure if you're familiar with that work. The differential privacy removes outliers automatically. So yeah, this is something we need to think about in the specific scenario, but there are a lot of scenarios where that's very reasonable, and social scientists who go and hand out surveys are definitely no more defended against that than us.
Thank you. That was a great talk. I had a question kind of related to this. So in terms of thinking of an application of this, what kind of application? So I'm just thinking from what would be the end computation that users would be interested. What kind of, so survey and statistics seem the reasonable ones. Are there other examples? I think would be great applications for a small focused group of users they are interested in.
So again, surveys and statistics I think is a massive one. Again, this can be used also for end users providing their own one data point, but it could also be used by multiple organizations to carry out a global type of research. I actually am thinking of more social science and social welfare type applications, because these are applications where we don't have solutions for. No one and there's a lot of social benefit in running these. So I can think of a lot of those type of scenarios, but I guess in my experience with MPC, once we have tools that are available, the applications come from elsewhere, and we're very surprised at them. So let's make the tools, and then people will come to us with their applications, I'm sure.
Thank you.
So this is a question related to the idea you mentioned about solving the problem of having everyone up at the same time. So you're proposing to have like a cloud instance allocated for you to do the job for you at the right time, right? So I think one of the natural questions is what about having people broadcast their inputs at whatever convenient time is for them, and everyone else, when they come up and are ready to participate, they just take that input and then use it. So in that case, you mentioned a lot of number of places, like people in Australia or in Europe or someone in Palestine, for example, being able to just join whatever time is convenient for them and just participate without having to.
The question is, who are they broadcasting it to?
Okay.
You have to have someone you're not going to broadcast a plain text value, so you want to broadcast secret shares. It's possible to think about a situation where there are parties who have registered, and if I trust a subset of those, and I could broadcast my input to, I could secret share amongst those, as long as I trusted at least 2/3 of those are honest. But it requires a stronger trust model. It's something which is certainly possible to do. You could think of a Tor-like thing where I can choose 3 servers en route. If I see this list of 10,000 participants there, then I can choose a subset of who I would want to share with, and then they would be willing to run that for me. That would certainly make sense.
So
since we have a registered process, then that would actually work.
Okay. So with a pre-processing or a registration phase, where people get the key material they need.
Yeah, so I could, at the registration phase, I could see who else is already registered, and if I was trusted a subset of those, I could say I want to share with those, and if they agree, then that would also work.
So just one more comment. So there is also the issue in some use case scenarios where you have people participating in a multi-party computation, but for some reason or a subset of the people are dishonest, and so the way they try to break the system or prevent it from working properly is not by feeding malformed input, but also to refrain from providing the input at the right time, and including additional delays, etc., just to prevent
So the system itself will generate the circuit and the execution environment by the people who actually turned up. So if someone, also just to relate, if someone didn't turn up by accident, that's not going to prevent everybody from running. Follow-up work that we're looking at now is dealing with guaranteed output delivery in an efficient way, possibly in a mixed model of malicious parties, but also honest parties that may fail by accident. We wouldn't want everything to stop before that, but that's something which we do need to deal with.
All right, thanks.
I think we're over time already, so we'll have to take the rest of the questions offline.
Thank you.